thanks for this opportunity to present our work over here. I'm Jaya Kumar from IISc. I'm part of Animesh Kule's group at IISc. So today what we'll look at is the gyrokinetic simulation, which actually was very well motivated by Professor Ganesh on the first day, the second talk. And what we will look at is turbulence, optimization, and so on. But mainly using this as a tool to analyze some of the experiments that's being carried on. So PTG is, you must have met quite a few of our students in the posters, right? So we have a big enough group, almost half of them are here. Typically, we work on problems related to Tokamak as well as Stellarator. I think we have never discussed Stellarator on this conference. So that's good, we'll get into that part. But here we will typically use this code called GTC, right? Then there is one more set of problems that so that is more like a physics problem. We use GTC as a tool to analyze physics problems. Whereas the other part that we work on is development of this code called G2C3. So my focus is mainly in developing this code. I am more of a computational physicist. So in case you have a tough physics question, I will deflect it to Animesh, right? So he will take care of it for me. Other than that, we are also looking at how to get into this optimization of Stellarator problem, because this seems to be a hot topic. A lot of people are looking into this because in terms of private sectors, people are interested in these kind of problems. Okay, in terms of motivation, why it looks like turbulence is one of the main problem in fusion, right? Typically, most of us talk about turbulence as a topic to work on. But here is a good problem wherein unless you kind of have a good handle on turbulence, we may not be able to solve this problem, which is very much important for us. And we will work with the gyrokinetics. It was motivated to some extent why we need gyrokinetics. The initial idea was that I would give this as a, a flash talk for all the posters that our students have so that I can motivate you to go and look at it. But ironically, I am the last person. Poster session is done, but I'll still stick to the plan. So instead of giving the punchline for the poster, I'll give some punchlines from the poster, hopefully. But more, it's still a motivation towards a problem, right? Okay, so the way we'll go about it is this. One thing that, okay, so start off with turbulence. Again, as Professor Ganesh pointed out, if you don't include turbulence, the rate at which the plasma would escape will be 100 times lower than what turbulence tells us. So without turbulence, we may not be able to match the observed results. And then there is, it looks like all the confinement problem, the profile, the operational limits that we encounter in experiments, for that without turbulence, we may not be able to access or understand them better. Also, we need to work with kinetic modeling. Now, turbulence is a problem because we haven't solved it, but numerically also it's still a problem. If you look at it, turbulence is a multi-scale problem. It's highly computationally intensive. Go to any supercomputer and look at what is the code that is running with the biggest code that is running. Typically, it's a turbulence code, or it might be a ML code right now, I suppose. But overall, we are trying to look at how the plasma is going to escape and how do we try to control it. And why the plasma is trying to escape? Here you see that there is huge amount of gradients. If you look at temperature at the core to the edge, a huge difference in temperature, right? Typically 10 times the sun's temperature at the center, and outside at the boundary it has to be of 100 Kelvin or so. And then there is a density gradient as well. And along with that, there is something called a zonal flow, which we'll try to get at, okay? Which is a kind of a non-trivial thing that happens along with turbulence, a nonlinear phenomenon. Gyrokinetics, again, it turns out that fluid is not good enough for our problem, especially in the core region. You need to handle the Landau damping, zonal flow, trapped particles. All of these fluid model wouldn't be able to capture. I mean, you can modify it, modify a fluid model, but it's not effective. we are trying to do a gyrokinetic model, so we are going to integrate out. So typically a charged particle in the presence of magnetic field will have a gyro motion, but instead of that, we want to look at simplify the model and look at the effective motion of the whole thing. So if you try to, this is the only equation that I'm going to show to you today. Gyrokinetic lasso equation, all of you must have seen this, but we will work in a limit of collisionless. So the right-hand side is 0, okay? So what can we look for? And of course, we would do particle in cell simulation. There are other ways of going about it, but we'll stick to this. Coming to the punchline, okay. I will present two sets of styles of working, right? One is using GTC, another one is G2C3. When I say style, this is important. Typically, I have worked in multiple groups. Typically, when we work on simulation, we tend to cook up problems, right? And try to motivate it based on what we like. But in our group, the trend is very different. We literally go to the experimentalists and ask them, what is the problem that you're trying to solve? We are literally acting like a doctor. Tell me what's the problem, and I will try to solve it, right? That's the way we go about it with the first case. And G2C3 is development, so that's where we do a typical simulation kind of approach. Okay, looking at different problems. So I will give you some snippets of different problems, the posters that were presented over the last few days. So this is one of the problems. This is from D3D. And just like how an engine has different modes, you have a sports mode or eco mode and so on, Tokamak also seems to have different modes of operation, right? And here is one particular mode wherein there is something called edge localized mode, which is like a pressure cooker. Like from a pressure cooker, the pressure gets released intermittently. Something similar happens in these kind of systems in this particular mode, which can be good or bad. Here's the problem with this field, right? You can never say something is good or bad. Whether elms are good or bad, we don't know. I'll give you more examples as we go along. So anyway, for this particular problem, experimentalists tell us that it is bad for them to have elms. So they managed to find a regime in which they could suppress it. And they give us the profile. So typically, they would give us the temperature profile as well as the density profile. And we go as well as the geometry of the magnetic field. You take it as an input, initialize your code, and run the code. And look for what the code tells you. And typically, you can do linear kind of simulations. You can get instabilities, different instabilities. You can study different instabilities. So here, for example, we've studied how so if you look at this temperature, you find that the ion temperature is higher than the electron temperature, right? So they are not equal. They are not equilibrated. We can get into a discussion over that, but here that's the case. And this is because of the way you heat the plasma, whether you heat the ion or electron. And here it turns out that the ions are heated. But if you want to go to a different system, for example, ITER, they would preferably like to heat the electron. Then they would want to know if the temperature of the electron was higher than the ion, how will it behave? So that's the kind of study that we performed over here. We tried to look at, okay, this is what you do. You want the simulation to be able to do, right? But then it is motivated from the experiments. They tell us that what should you look for? And this is what we look at. And typically, you will get some kind of a turbulence structure and so on. This is typically what happens. You start with some kind of a linear phase, wherein a particular wavelength starts off in the linear regime, and once you get into the nonlinear regime, that's the time evolution over there, it gets saturated and gets into a turbulent regime, wherein you get multiple modes, right? That's the typical picture that you have. Fine, then, but it turns out that if you look at this carefully, instead of looking at that particular simulation, let's look at a much more simpler case. You'll find that you'll see something special happening over here. You'll see these band kind of structures, if you observe carefully, right? These are what are called as zonal flows. So these are something called as k equal to 0 modes. Okay, these are what you would observe in the case of Jupiter bands and so on. And these are important. It took the community quite some time to realize that zonal flows are important. That's a long story, but overall, you can, in simulation, you can suppress it and try to see what is the effect of zonal flows, right? And so that's what's shown over there. It turns out that if you have zonal flow, which is the case over here, the transport, the diffusivity gets suppressed, which is good, which is what we want. And what gives rise to the zonal flow is basically the symmetry. It's a torus, okay? It has got a rotational symmetry. Now, what happens if the rotational symmetry is broken, as in the case of a stellarator? So here is the old stellarator, 98. It was built in 98 in Spain, and we wanted to study some other phenomena. But to start off with, we will typically do a simple linear stability analysis and linear problem, as well as look at simple ITG, so-called ITG modes and so on. And here, when we check whether there are zonal flows, it turns out that zonal flows are absent. That was what was expected, so nothing new. Again, if you tell this to a simulation person, they will say, what's the big deal? We knew it beforehand. But for experimentalists, it's always in the eye of the beauty lies in the eye of the beholder, right? For experimentalists, when you show this, for them, you are the first guys to show us that, yes, this actually is true in our machine, right? That makes a huge difference. That's the reason why you should always talk to the right person, right? If you just talk among yourself, no, that's not good enough. Maybe you're doing very well, you don't know. So, okay, so that's how the TJ2 works, but that's wherein later on, all the newer versions of these stellarators, what they tried to do was, they tried to build these systems such that can we get back these zonal flows? How do we get back these zonal flows? So there were different kind of schemes that people cooked up, some kind of a quasi-symmetry, right? Quasi-toroidal symmetry. There are different ways of implementing, and that's how they initially designed this W7X, which is a good stellarator which is running in Germany. But recently, they also came up with another design. So these are optimization. They are trying to play around with how can we incorporate these symmetries back into the system so that it shows zonal flows just like a Tokamak. They want to get similar behavior like Tokamak, and that's what they observe. So W7X, it was already known, and QSTK was a new design which they are planning to build, I suppose. So we basically made use of their data in collaboration with them, and we studied the effect of zonal flow. So that's where you can play around with the optimization. How do we incorporate this symmetry or the geometry within the problem, right? So that's one way of going about it. Now I'll completely switch gears. When we were working on this, Joydeep from IPR suddenly calls up and says, okay, we have a new set of results, completely non-trivial. And what's the non-trivial result? They actually, when they puff gas for fueling the fusion in the generation of the plasma, they found that when they puff gas at a room temperature, of course, the density gets changed. So this was the initial density. When they puff gas from the exterior, the density profile changes. Okay, it gets flattened and so on. But if you look at what happens to the temperature before and after, remember, we are introducing puffing gas of a lower temperature at the boundary. It turns out that at the core, the temperature increases. So you are literally heating the system by puffing gas at the boundaries. How good is that? So this is something that they observed. They already had some ideas to what's happening, and they wanted us to reconfirm using simulation, and that's what we did. So we basically ran our simulations with the linear, nonlinear turbulence, and so on, and we show that, yes, the turbulence is suppressed after the before and after refers to before gas puffing and after gas puffing, and it turns out that the turbulence is reduced and it's localized, which is good. So this is something that we worked on, but as well as you can study the diffusion and so on. Before it was higher, then it came down. Similarly, this is where it is non-trivial. The way people started working on looking at impurities is, you would imagine that adding impurity to plasma is bad. It might diffuse the whole system, right? But recent observations show that you add impurity, it confines the system better. This is somewhat analogous to how semiconductors are kind of becoming useful, right? Are useful. You add impurity, it improves some of the properties. Something similar is happening, again, completely non-trivial. So we are also studying different kind of impurities, adding argon, tungsten, and so on, right? Not just because those are impurities coming from the container, but it turns out it's good. Okay, again, I'll switch gears. I'll come to the G2C3. So G2C3 is a code which we have been working on for last 6 years under development, and there is a particular motivation towards it. I won't get into it here, but overall, it's to support our own local fusion program, as well as to extend the code applicability. Here is some mandatory slide we need for a G2C3 code. It is a particle in cell code. We use MHD results to start the simulation. Then it's a 5D gyrokinetic code, and so on. But importantly, we make use of a neural network to perform something, some part of the calculation. And I think it is indispensable. Okay, when we started off, it didn't sound like that, but now it turns out that actually simply makes the life easier to go ahead and solve this problem. Okay, I will just give you an update. Again, I have talked about this G2C3 at multiple places. I will not get into that. But just to give you an update as to what's happening within the code. So this is what we started off with, linear ITG simulation, ion temperature gradient simulation. This is what we had initially as a test. Right now, we are incorporating the nonlinear effects as well as the zonal flow. This is something some of our students are working on. Again, zonal flow, it turned out that our implementation is wrong, so that's why it's in bracket right now. As well as those were kind of incorporating extra modules to keep on growing the code. Parallelly, we also need to test our code on some physics problems. So here is one particular problem wherein we took a magnetic island which was observed in Aditya, and we tried to model it. But strangely enough, which is typical, in most of these experiments in Aditya, they can't measure this so-called flattening of density. So when you add this extra island, typically the density has a flattening, this kind of shape. Ideally, they should be able to measure it, but it turns out that they have some problems with the measurement. So we kind of came up, not our own idea, but something which was used earlier, by which you could modify the profile, the density profile, and then run the G2C3 code in a self-consistent manner. That was a non-trivial thing. It took us some time to wrap around our mind about it. Okay, so that was one of the physics results that we have, which we'll soon put up on archive. I hope Vibhor is happy about it. And the other thing that we have managed to do is the scaling. So this is what I'm actually proud of. We never meant it to be so good. So here is a case wherein we are running it on 400 nodes. 400 into 48 or 64? Okay, I don't remember. Each node has 64 cores, I suppose. So this is in Param Pravega. This is the IISc supercomputer. Literally, we made use of the whole supercomputer. I think the total number is 420 or 428 or so. We literally ran the code on the whole supercomputer, and we found that still it was working well. It didn't crash. Okay, which is not a straightforward thing for a code. And looking at this, meanwhile, we are also parallelly trying to build a GPU version, because it turns out that most of the current codes are GPU versions, and they seem to perform far better in terms of time, computation time. But then you need huge number of GPU cards. So it's a give and take problem. Okay, but it turned out that the scaling, looking at the scaling, our collaborators from CDAC, they actually asked us to perform the scaling work on a newly installed Param Rudra in IIT Bombay. And they were so impressed that they made use of our code to build their reports, and now they are planning to replace the LAMPS code, which is a typical molecular dynamics code, which is used for scaling purposes in all these supercomputers, with our code, which is great. Again, I suppose one of this is Make in India is playing a role over there, but that's fine, right? So this is how it's progressing right now. And all of this is not possible without a huge set of collaborations. You must have seen all our posters with tens of authors, right? It makes a huge difference to have these set of collaborators. It's a proper collaborative work wherein we get data from experiment and try to incorporate as much detail as possible within our simulation. And we learn a lot from experimentalists. So this is something that I think all of us should learn, that I'm sure all of you know, but still, just to emphasize, talk to experimentalists. It makes they have different understanding of the problem, right? And that makes that gives you a different point of view, different understanding towards the whole thing. Right, so these are the different set of collaborators that we had over this period of time. And of course, I should thank the computational facilities at IISc and at IPR as well. So with that, I stop over here. Thank you for it.
Very nice talk. So we have enough time for questions.
Yeah.
I am Shishir Purohit from IPR. Basically, I am a diagnostician.
Okay.
Experimentalist.
Right.
So can you visit to your slide number 28?
50?
28, 28.
Okay.
Okay. So as you mentioned that you have observed the flattening of the density profile,
right,
which is attributed to the islands
right,
available. Can you comment what is the typical width at the density profile is flat?
Okay, so I think we talked to Deepthi madam about it, and they suggested that it's 6 centimeters. Is that right, Vibhor? Right, 6 centimeters. That's what.
So it is 2-1.
Sorry?
This is island 2-1.
2-1, right.
So 2-1 is having a width of almost 6 centimeters.
That's what was given to us.
Okay.
Yeah. So I suppose you have a better idea about what's the measurement. Okay, fine. Yeah, sure.
Yeah.
Hello.
Yeah.
So I'm Vivek from VIT. A great talk, sir. Could you go to slide number 20?
20.
Basically where the Aditya U Tokamak diagram was.
Right.
This one, yes. So here, in the beginning you said the asymmetry of the shape of a tokamak usually introduces zonal flow.
Right.
And I'm asking, because of that, in this diagram, the hydrogen gas is only pumped from one side of the tokamak, like in this diagram here.
Okay, okay.
Is that introducing essentially a zonal flow which is responsible for the temperature increase?
Right.
Yeah.
Okay.
That is my question.
I'm not the right person to answer this. I think, yeah, can you?
It's a representative model, and
right,
yeah, so
it's pumping symmetrically. It's not like that, right?
there is no such question of symmetry or asymmetry,
okay,
because it is, of course, from pumping from the outside or inside will be different for the confinement purpose, okay, but the locations in the outboard side will not matter.
Okay, thank you.
Yeah, this is a schematic. So a lot of things over here were schematic. I refuse to put the complete details.
Any other question?
Hi Jaya, Kaushal from IVR here. So you mentioned that edge localized mode in
right,
QH mode regime
right,
is generally bad for machines, since it's a lot. Since it brings a lot of heat and particle flux to the machine wall. But you also mentioned that it is sometimes good for some experiment and discharge.
right.
So can you explain how it good for some discharges or experiments?
One advantage, one reason why they want ELMs is if they have impurities within the system, they want it to be discharged. They want them to be dispersed out of the core. Then they would like to have ELMs. So I think even when they say QH, it doesn't completely get rid of it. Is that right, Abhishek? Yeah, it's suppressed, but not completely. I don't think getting rid of it completely is a good idea. That's the thing. It's always there is a good part to it, bad part to it. It's about finding a middle ground.
Somewhere you mentioned by injecting impurities.
Right.
you can control the density by like hydrogen or any other impurity that you think of like.
Right.
So what is the understanding that like in introducing an impurity, let's say like maybe macroscopic impurity,
Right.
not the gas, but any other impurity.
Right.
So why it would actually change the density?
Oh, okay. Why that would change the density? Okay, not the just the impurity. Okay. Okay. I don't think I have a good answer. Animesh, is there anything?
The what happened, I mean, what is our understanding? Maybe experimental people can tell better. I think like maybe you also. See, one of the understanding is like if you inject any of this impurity from outside, what we found that somehow the major instability which was driving the energy and the particle outside, so they get suppressed. And I think the profile modification is one of the main role which is playing here. So once you have control on the instabilities, so basically the amount of the particle flux which is going outside is reduced, which possibly is the reason for improving the density profile in the core region. So that is the way we look into like this way. But maybe there will be some better experimental perspective into it, so that we don't know.
I could understand when it is hydrogen, the same
Yes.
plasma, when particles.
So for
and it
argon
ionize
also we
it,
found similar observations also.
It changes the density profile.
No, for argon also we found, even in Aditya. we
Argon
found.
also, they can
Yes.
ionize
Yes,
very
so it's the
easily.
same
But
things
if you
that we
have
also
like
found.
other particles, like,
Yeah.
you know,
So
they
if you
may
go
not
to the
ionize.
high Z, we don't know what will be the things. But at least for argon and hydrogen, we found this is quite a common things available.
Thank you, Jaya, for a nice talk. So from a code developer to a code developer, so how do you actually integrate that in your GTC? I would like to understand the underlying numerical scheme that you do for your GTC, for let's say.
You mean G2C3?
No, GTC, the earlier one.
Right.
The Vlasov solver you use, right?
Right.
Collisionless Vlasov solver.
Right.
So what sort of numerical scheme do you use?
Oh, okay. So so this is a particle in cell. So it has both Poisson solver as well as a particles. So it's a RK2. The particle dynamics is RK2 and the Poisson solver is finite element.
Yeah, but this is where my question is. See, RK2 are not symplectic solvers. So
Right.
how do you ensure energy conservation of your particles for non-symplectic solvers?
Right, exactly. So that's wherein we have these diagnostics, wherein we also verify how the energy behaves, and typically we choose the delta T to be good enough, small enough that it remains conserved. That's some diagnostic that we always keep observing in the
This
simulation.
last one, is this code GPU variant?
GTC has a GPU version as well. Yes. it
Okay,
has.
great. Thank you.
Thank you, Jay.
Thank you.